This video is going to cover concept 3 in our notes, which is incline Atwood machines. First of all, I had not written this onto the notes, so take a minute to write down the problem. If m sub 1 is 7 kilograms and m sub 2 is 9 kilograms and the angle of incline is 40 degrees, find the acceleration of the system. Assume there is no friction. So once we do this, we of course want to go through and make our free body diagram. I'm going to put our 40 degrees in here also. So in our free body diagram, we have on M1, we have gravity acting downwards, of course. We have the normal force acting perpendicular to the ramp. And then our gravity, we're going to break up into the X component and the Y component. The gravity acting on mass 1, it is 7 kilograms, so it's 7 times 9.8, and 7 times 9.8 comes out to be 68.6 newtons. So we have 68.6 newtons there. We also want to find the force of gravity acting on the other mass, and that mass is 9 kilograms times 9.8 is 88.2 newtons. So we have that gravity working in that direction. We do have the tensions. Those tensions are going to cancel each other out while we're talking about acceleration, so we don't actually need the tensions to talk about acceleration. To find acceleration, that's when we want to do the sum of the forces. The sum of the forces divided by the total mass. So the sum of our forces, we have 88.2 newtons acting downward in this direction. And the other direction, we need to find what is the force acting this way. And that is this Fg of x sub x here. And so Fg sub x, that is across from that, so it is going to be 68.6 times sine of theta, or sine of 40. So if we take a minute to put that into our calculator, 68.6 times the sine of 40, that comes out to be 44.1 newtons. It's actually 44.095, but that does round up to 44.1. It is a coincidence that these two values are almost exactly half of each other. That's just a coincidence. Don't let that throw you off. Okay, that is the force going in down the ramp, and then this force is coming this way. And so the sum of our forces, well, we have an 88.2 Newton force going in one direction, and we have the 44.1 Newton force going in the other direction. And our total mass is 7 plus 9 kilograms, or 16 kilograms. And so when we do our subtraction, and again we have estimated with our decimals here, so we're going to have 44.1 divided by 16, and that comes out to be 2.756, or we can call that 2.76 meters per second squared. And we might take a second to talk about which direction it is going. You might want to call that negative. I'm just going to say that it's going in the clockwise direction. So that's how we find the acceleration. The next part that we want to look at, the next question we want to look at, is to find the tension in the string. To find the tension in that string, I only want to look at one part of it because I only have to look at one part of it. The tension in the string is the same throughout. It's the same on both sides. And so I really only need to look at one of them to determine the tension in that string. So I'm going to choose to look at my mass 2, because mass 2 is going straight up and down, which just seems a lot less confusing than trying to deal with the angles. So I have the force of gravity on mass 2, and then going in the upward direction, I have the force of tension. Now the other thing that's going on is I have this mass which is accelerating in the downward direction. And remember that what we've talked about is, I'm going to write this out here, is that if the object is accelerating downward, that's kind of relieving some of the tension off of this. And if it's going down, we want to go ahead and subtract those because it's relieving that tension. If it were accelerating upward, that tension would be much tighter because it'd be pulling up on it, and so we would add those two together. In this case, it is going downward, and so we're going to subtract them like this. So our force of tension, mass times gravity for number 2, which is 88.2, and mass times acceleration, which is 9 times 2.76. And so our tension is going to be 88.2 minus, and I get 24.8. And so if I subtract that, I get 63.4. So my force of tension is 63.4 newtons. That is example 5. Just to recap a couple of things, when we are finding the acceleration, the sum of the forces we're subtracting because they're going different ways, but the total we add because we have to include that whole thing in our system, we get our acceleration. Once we get our acceleration, we use that to find the tension, and we're going to, another way, I didn't write this out, but remember I could factor out that m, and I could say g minus a, and this is what we had on the other page of our notes earlier. So it's because it's going downward, that acceleration is being subtracted away from the gravity. All right, we have the same exact thing going on, the same exact scenario. So I'm going to take a minute just to put in some information. Okay, this is some information that I just carried over from the previous page. So here it is sort of off to the side, and here it is on the diagram itself. On this problem, what I want to do is I'm given some information about coefficient of friction. And so the question is, what is the coefficient of friction that is required for the block not to slip? So if it's not going to slip, its acceleration is going to be 0, which means that our net forces, our sum of our forces, is going to equal 0 because it's not moving. And so we just need to figure out what would that take. Well, let's go back to our diagram, our free body diagram. As it is now, it is getting pulled. And that is because the mass 2 is larger and it has more force and it's pulling it, and so it's getting pulled upward. If it is getting pulled upward, then the force of friction must be acting down and to the left on the ramp. So in other words, we're needing to find out how much does this friction need to be to counteract the force that is going on over here. And so when we do this, let's take a look at what we have going on. We have a force of 88.2 going this way. We have a force of 44.1 going this way, and we want to know how much do we need to add to that to counteract that 88.2 Newton. So let's take a minute to set this up. We have 88.2 newtons on going one direction. It doesn't matter really if we call that the positive or negative. Let's just call that the positive. And because what we want to do is for the sum of the forces to be equal to 0. And so going the other way is we can call that down. If we're calling this plus, let's call this minus. So we want to say, okay, that if we subtract out the frictional force, and we also have to subtract out that 44.1, that's going to add up to be 0. Again, it is coincidence that 88.2 and 44.1 is exactly half of each other. This was actually 44.095, but that was coincidence. But let's go ahead and simplify. So 88.2 minus 44.1 is 44.1. And if I add my force of friction to the other side, then what I'm saying is I need 44.1 newtons of friction to stop it from moving anywhere. Okay, well, let's think about friction. We have an equation for friction that is this. And so now what we need to do is say, okay, and it doesn't matter which one from here you go with, let's just maybe keep with where we are. We have 44.1 newtons, and that is supposed to equal the force of friction. Well, the force of friction is mu times the normal force. And the normal force is 52.6. So I have 44.1 newtons is equal to mu times 52.6. And so I need to divide my 44.1 divided by 52.6, and I get 0.838 as my coefficient of friction. So mu is 0.838. Because what we're saying is How much friction do we need to stop it? That has to be sum of 0, and so we need some extra force, which is our frictional force. We're saying we have to have something pretty high friction. 0.8 is a pretty high friction in order to stop it from moving. That is the end of the Atwood notes. We will do some more examples in class.